Hello, Algebra 2. This video lesson is about logarithmic functions that are known as logs. Let's start by talking about why logs exist in the first place. Of course, you know that 2 squared is 4 and 2 to the third, or in other words, 2 cubed is 8. But what if you were trying to figure out how 2 to the x could be 6? In other words, some exponent in between 2 and 3 that gets you the resulting value halfway between 4 and 8. Well, in order to find those exponent values that aren't obvious, mathematicians defined a new concept called logarithms. Logarithms are simply exponents, exponential equations I should say, written in different form. As an example, and a classic example here, 2 to the 5th equals 32, would be rewritten as a log in this way. And this is the way you would say it as well. Log base 2 of 32 equals 5. Notice I've got all three of the same numbers that I have here, simply jumbled in a different order. Well, it's not really a jumble though. I said log base 2, and remember back when we first started talking about powers, we said that the 2 here is the base of this power. So 2 has remained base in both forms. And really what's changed place is the exponent and the result. You've got base and what used to be the result equals what used to be the exponent. That's the change that's happened here. So for example here, 5 to the 0 equals 1. Rewriting that as a log, it becomes log base 5 of 1 equals 0. So in fact, all you're really doing is you're changing the position, as I say, of the exponent and the result. C, as an example here, becomes log base 10 of 10 equals 1. D becomes log base 10 of 0.1, or 1/10, equals -1. And the last one there, in logarithmic form, becomes log base 1/2, or log base 0.5 if you prefer it as a decimal, and you can write it that way. Log base 1/2 of 2 equals -1. All right, moving on from that example. The definition here, I'm not going to read the whole thing. You're certainly welcome to hit the pause button and read this whole thing to yourself. I just want to hone in on this. Remember, the way you say this is log base b of y equals x. And the definition says this is true if and only if, or in other words, when, b to the x equals y. So in other words, simpler way of saying this, if the log base b of y is x, then b to the x has to be equal to y. Vice versa is also true. So if you know that b to the x equals y, then you know the log base b of y is the same thing as x. Examples tend to make this clearest. I've talked about these examples. I did forget to mention, or highlight, I guess I should say, 2 particular examples from the slide 2 slides ago. B and C here, where we say log base 5 of 1 equals 0, and this one, log base 10 of 10 equals 1. If the result of your log is a 0 or a 1, well, let's talk about the specifics of that. Anytime that the result of a log turns out to be 0, remember that had to be true because b to the 0 power is equal to 1. And maybe more interestingly, anytime that the base and the thing you're taking the log of are matching, they're going to be, the result, the end result, is going to be 1, and that's because anything to the first power is itself. So the base and the result here match. In this case, the exponent on the power is 0, and over here the result was 0. Okay, enough explanation. Let's talk about some examples. And here are 4. I'm going to have you evaluate on your own each of these. You should not need a calculator to do any of these. I haven't told you how to do logs on a calculator. I will later in this lesson, but if you already know, still set the calculator aside. Don't use that to figure this out. Just remind yourself that if you're trying to find the log base b of y, what you're really doing is trying to figure out what power of b, in other words, what exponent do you need to put to b in order to get y. So for a here, what you're really asking yourself is 3 to what power is going to give you 81. And here similarly is b written in that form. Hit the pause button when you come back. I'm going to show you all 4 answers and talk you through them all. Okay, I'm going to assume that you did that. Let me just show you a and b first. You have to raise 3 to the 4th power to get 81. So to write it as a log base 3 of 81 is equal to 4. That's the solution, the evaluation of that logarithmic expression. Similarly here for b, 0.04, just remember 0.04 is the same thing as 4 over 100. Simplified down, that's 1 over 25. Well, if you want to turn 5 into 1 over 25, you have to raise it to the negative 2 power. So log base 5 of 0.04 would give you negative 2. Negative 2 is that exponent you were looking for. All right, now for C and D, if this is making more sense now, hit the pause button again if you need to, and rethink C and D. I'm going to assume that you're ready to see the answers to C and D, and there they are. Half to what power gives you 8? The power you would need would be negative 3. So in other words, log base 1/2 of 8 is negative 3. Similarly, 9 to what power gives you 3? Well, that power would have to be 1/2 or 0.5. So in other words, the log base 9 of 3 is equal to 0.5 or 1/2. Using calculators, like I promised. Most calculators, certainly graphing calculators, have the log button and the ln, or natural log button. Later I'm going to talk about what ln means, but for now, if you had to put log of 5 into your calculator, well, with a graphing calculator, all you would do is type in log 5, enter, and you should get this as your result. Make sure you do. So test that out with your calculator. Natural logs. Well, why don't I first, at this point, talk about this difference. Notice there's no base here in this statement, log of 5. Well, the assumed base, if it doesn't say the base, is base 10. That's the base that we're all used to working with, is base 10. So this is actually saying log base 10 of 5, but you don't have to worry about that 10. It's the most common situation that we deal with when we talk about logs in formulas. The other most common situation is base e. Remember e that we were talking about from just chapter 8.3, the most previous section of the textbook. So ln of 0.1 is really saying log base e of 0.1, but you don't have to worry about that when you're doing it. You just hit the ln button, ln 0.1, enter. You should get this result. Make sure you do. If you don't, then come in and see me, and let's make sure that we're using the calculator correctly. Okay, so let's think about how to put this to use. Hit the pause button, read this paragraph to yourself, and when you come back, I'm going to talk you through it. Okay, all this formula is saying is that the slope of a beach, which is s, is equal to this constant, 0.159, plus this coefficient times the log of d, the logarithmic of the diameter of the average sand particle. Okay, so somehow or other, somebody went to your favorite beach and measured the sand particles and found that the typical diameter of a sand particle there is 0.25 millimeters. Well, this makes some sense, right? Depending on the sand, you probably never thought about what was the characteristic of the sand, but some beaches are way steeper than others. It turns out that it's a function of the diameter of the sand particles. It's how big those particles are. Well, how would we make use of knowing this? Well, all you have to do is plug 0.25 in there for D, and you'll use your calculator for this. And so it's going to look like this. You plug 0.25 there into this statement, and now it's just a matter of using the calculator. 0.159 plus, well, the log of 0.25 is roughly negative 0.602. And so that times that plus 0.159 gives you 0.09. The slope of the beach is about 0.09, which means, in other words, remember, slope is rise over run. This is a very gentle slope that only goes down 9 meters for every 100 meters that you walk out toward the ocean. So it's a very gentle, shallow, sloped beach. Okay, that's it. That's all that I want you to know at this point about logs. Come into class with any questions you have about them, but otherwise we're going to move on to the next section with the next lesson.